Okay, so let's go through the solution. I'll draw the truth table for each of these and we'll see which one each is. So for the first one, P implies P. Well, there's only one variable P. It's either true or false. Well, 0 implies 0. That's certainly true because false implies anything. 1 implies 1. Well, that's true because if true, then true is a true statement. So, sorry, that drew a 0 before. That's not right. False implies false is true. True implies true is true. So it looks like this one is a tautology. Which makes sense, right? If P is true, then P is true. It's not a very useful statement, but it's certainly a true statement. Let's look at the second one. If P or Q, then P and Q. Alright, so let's draw the truth table. Intuitively, just from my gut feeling, this doesn't feel like it's going to be a tautology, because if P alone is true and Q is false, it doesn't follow that they're both true. So we should expect that this is not going to be a tautology, but let's draw the truth table and find out. 0, 0, 0, 1, 1, 0, 1, 1. Okay, P or Q is going to be this, 0, 1, 1. P and Q is going to be 0, 0, 0, 1. P or Q implies P and Q. False implies false is true. True implies false is false. True implies false is false. True implies true is true. It's sometimes true and it's sometimes false. This makes this a contingency. I almost certainly spelled that word wrong. Yeah, drop the N. Contingency. Okay. P or Q implies P, X, or Q. Well, I'm just going to keep using this truth table here to avoid redoing a lot of work. P, X, or Q. So when the inputs are different, so these two, so 0, 1, 1, 0. And then P or Q implies P, X, or Q. False implies false is true. True implies true is true. True implies true is true. True implies false is false. Okay? Again, it's a contingency. Because there's some cases where it's true and some cases where it's false. P and not P implies Q. So if P and not P, then Q. I'm just looking at this statement. This feels a bit nonsensical. This feels like it ought not to be true because the left-hand side has really got nothing to do with the right-hand side. But in fact, we will see this is a tautology, and this is a very interesting kind of tautology. The reason why this is a true statement, because the left-hand side of the implication is garbage. It's always false, right? And when you assume false, you can derive anything from false. So let's see. So I'll draw my truth table. P, Q, 0, 0, 0, 1, 1, 0, 1, 1. P and not P, so I need to compute not P. Well, not P is the opposite of P. 1, 1, 0, 0. P and not P. 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 0 is 0. So P and not P is the same as just the statement false, right? Because it's never the case that both P and not P can simultaneously be true. And then we have Q. Well, there's Q. And so now we want P and not P implies Q. Well, the left-hand side of the implication is false, which means this is going to be true regardless, right? False implies false is true. False implies true is true. Well, false implies anything is true, so these are all going to be true. So it is indeed a tautology. This sort of equation, or anything of this form, is sometimes called the principle of explosion. Explosion. Which is sometimes written as false implies P. That is, if you assume something false, you can derive anything. Which makes sense, right? If you assume garbage to begin with, you can just make up whatever you want. And P. Well, P alone is still a valid Boolean equation, right? The truth table of it isn't particularly interesting. P, 0, 1, and that's it. So if P is false, then P is false, and if P is true, then P is true. So it looks like the statement P alone is a contingency. Which makes sense, right? The truth value of P depends on the truth value you assign to P, right? If P is false, it's false. If P is true, it's true. So that makes the statement P alone by itself a contingency.